It's Terry Dennery, the MathWorks. So this video, we're going to focus on software, and very specifically lines of code that can calculate, I'll call it the dynamics, the motion, the mechanics, which really is not just motion, it's really motion plus forces and torques that drive all of it. And it's essentially what Simscape Multibody does, right? Now, I love Simscape Multibody because it works so well within Simulink. And it's got kind of what I need to, just kind of make sure that I'm getting it right too, and that I can apply it into controls and all that sort of thing. Um, so there's a little bit of, I'd say I'm going to be a little more deliberate as I talk about MotionGenesis in this video and to kind of explain the complementary nature that it has with Simscape Multibody, all right? Because at a surface level, they'll look like they're kind of doing the same thing. And if you kind of limit what you describe about each of them, you might say, well, one's way better than the other, okay? But really, they both bring important things to the table. All right, so anyways, it's called MotionGenesis Kane 6.4. It was developed by, I'll say, a group at Stanford University that originally was headed by Professor Thomas Kane, who came up with a great method of let's say, deriving the equations of motion for rigid body mechanical systems. And so one of his graduate students, Paul Mitige, was essentially working on his PhD at the same time as me at Stanford, and we became buddies for various reasons. And we've just really kind of walked into this over the years, and I think it's pretty good. Hopefully hopefully I'll be able to kind of convey the idea well, and hopefully you'll like what I'm showing. All right. So at its heart, it's a symbolic manipulator, and it is a MathWorks partner. So it's kind of featured on our website under third-party products. And I think through this video, I think I'll show you that it works really well. Here's the basic idea. MotionGenesis Kane is a fast, compact, highly advanced symbolic manipulator with expert tools for mathematics, code generation, and forces in motion. All right. It incorporates Newtonian physics and simulates the motion of mechanical, biomechanical, aerospace, and related systems. So anyways, without further ado, let's get into this. All right. And so I think I'll start here. So I created this new directory. I just want to do the fresh export one more time of the model that we created in the previous video. So I got it up and running right here. And let's go ahead and launch Get Geometry. Okay, so there's Simscape Multibody model. I always like to hit the run button right off the bat. And we'll see our robot in a second with the animation created with the STL files that were brought in from Simwise, right? But this video can be much more about these additional documents, these text documents. And specifically we'll get into this one called robotfd.txt. So basically, this is the input deck for MotionGenesis. Paul and I kind of came up with this cute name, CAD to chip, because we think the power of going from CAD, like SolidWorks, that on a fairly automated path that brings you all the way to a controller based on mechanics going to run on the embedded processor because you've generated code with Simulink. We think that's a very powerful, kind of path and can do all kinds of cool things with that. So anyways, we like that name, CAD to chip. The basic idea of MotionGenesis is, it's object oriented. We're defining an object that's what is a rigid body, but if you know Simwise, you probably can anticipate, Simwise and Simscape Multibody, you can probably anticipate quite well what's the nature of that object. And of course, it's going to be stuff like setting mass and inertia, and then there will be frames, coordinate systems that can be attached and positioned according to all these bodies as well. Again, it's kind of cool thing that object-oriented does for you. So we put all these frames on the bodies. Let's see. These are our part names, RIS1. Here are the frames we add to it. And then from there, we start creating the motors and the joints and things like that. And as we do that, we introduce the dynamic variables, like the motor Notice this, QRZTT motor double prime. Well, there is a single prime. You can see it right there even. And so, and then there is essentially without primes. And so that's basically acceleration, velocity, and then I'd say angle for that motor. And so each of the motors are kind of defined in a similar way. Then we get into ultimately setting gravity and essentially deliberate or explicitly setting, force is equal to mass acceleration, even though there's all kinds of geometry and masses and inertias that make up this assembly. That's the bottom line that you get down to, and that's where the dynamics and that's where kind of the, how the physics drives the motion of the system. And so our goal is to ultimately create a MATLAB file. Let's see that right here. Oops. All right. MG robot video underscore FD. FD is for forward dynamics. And so anyways, we just take all this. I'll just do Control A, Control C, and let's bring up MotionGenesis. And you'll see it's kind of, I'd say, well, certainly knowing Paul real well, Paul Mitigui, who authored all this, he was very inspired by MATLAB, and this kind of looks like what MATLAB looked like probably 20 years ago when Paul started doing, 20, 25 years ago when we started doing this. So, but anyways, we're watching kind of these calculations be made before our eyes. And what we end up with is essentially the equations of motion captured in the function that's right there. So MG robot video FD underscore or underscore FD for forward dynamics. So I'd say that I always do a little bit of grooming on this, and so I think I'll probably do it, but I'll give you at least an idea where I'm going with this. All right, and so essentially the states of the robot are going to be angle and angular velocity for every one of those motors. All right, the state can be constructed from those signals, those variables. Right, so these are going to be set up as inputs in a moment, and I'll probably skip through that just because it's kind of boring watching people code. All right, and then the outputs, they're already kind of loaded into this thing, this array called solution to algebraic equations. But I'm going to deliberately kind of put these all into the function statement too. But basically, here's what's going to happen, and I may edit it out just because I think it could be boring. But is these will be put into the function statement. I'm going to keep everything in radians. And so I'm going to just delete that. Okay. And most importantly, I'm going to put it in a MATLAB function block. So let's go here. Should then Control A again. So copy. Drag one of these in. It's going to have lots of inputs and outputs, so I'm going to make it pretty big. All right, and let me paste that in. All right, so now I'm going to go quiet for a little bit. I may even edit the next, 5 minutes out as I do this. I'm going to check my clock. I'm at 9:20 right now. So let's do this. Okay, so I'm 4 minutes into this, and you'll see that I got the function statement with inputs on velocity and position for each of those motors. It turns out that the turntable, I'll just say because of its geometry, its angle really has no influence on any of the other variables, and therefore all we really need is its first derivative dt. Okay, a little bit of a technical issue, but not that big of a deal. All right, and that the return of this function really is to return essentially the acceleration for each of those 5 motors. And there's one last thing I need to do. Here, I do want to show this though. So this is now kind of the new function statement, and that's what our MATLAB functions are looking like right now, is I do need to put all these torques in. And again, you could call it, let's call it user naivete, okay, as opposed to user error. But there's probably some way to do this a little bit better in MotionGenesis, but I'll just say that we got most of the hard part done, and I don't really mind so much. And so the last part will be to kind of set up all these torques as opposed to just showing up as and being set to a value of 0. Let's put those in as input statements too. All right, and oops, that's not what I wanted. So let me make sure I capture that better this time. So this one, okay, torque. And so basic idea is the torques will go in as inputs. Again, I'll be quiet as I kind of do this and delete kind of these settings of each of the torques to 0 that's taking place in the code. Okay, so it's 9:28. So now I have essentially the function statement the way I want. I got rid of the code that's going to convert between degrees and radians, can just keep everything in radians throughout. And the torques are now going in. And so as we back out, now we have all these inputs. So the torques at the top, then I'll say the position and velocity for each of the motor angles. Okay, so this is an algebraic thing. This is perfect for a MATLAB function. And so now we need to add the dynamics. And so I'll get my Simulink browser up, pop it out, close that. Let's bring this over here. And we will go to continuous. Now we could do this with discrete, and we will do it most likely later on. But for good, fast calculations, I love these second order integrators, which will take that acceleration and calculate both angle and angular velocity. Now again, for the turntable, all we really need is the velocity. And again, if it's really confusing, I'll do a whole video explaining what it, but I think it's kind of straightforward as you think about it. The angle of the turntable will not affect the dynamics of the other variables. All right, and so maybe we do like a terminator. Pop that on like that. We kind of like that number, and we will use it because we are going to report kind of stuff like this. So let's get that in, and let's do the same thing, bicep. Okay, so now we're at like 9:31. I got all the dynamics kind of hooked into it. Kind of ugly and messy to look at this level. Perhaps I'll clean it up a little bit, maybe make the lines a little more, well, whatever. Let's go create subsystem from the selection. Okay, and let's hit spacebar and just show that we're still up here with this one. Maybe I'll make them the same size block even at this level. All right, format. Match. Okay. All right, and I'm almost ready to do the comparison between the two. I mean, I can hit run now and we will get a calculation, but we are not reporting anything out of this yet. So we'll simply see compiling a little bit longer this time because it's taking all that MATLAB code and essentially compiling, converting it into something that's a little faster in its execution. That's part of a natural thing of Simulink. So, and there we go. All right. So let's report this information out. And I'll just call this TT. I'll put an RAD as for radians. And we'll do it for each of the motors. So now we have the outputs, and I'll do the comparison. I need to put in a bus selector on these guys. choose to report motion. Again, motion is kind of a loaded word, which to me means position, velocity, and acceleration. Oops. Hit apply. Okay. And I just want the position, and so I'm going to use a selector block to get that. I'll choose signal 1. Okay, now we have the means to compare them. All right, and so let's put in some scopes. Turntable to turntable. Okay, so it's run for 2 seconds. I'll run it from the scope. We'll look at the turntable scope. And that looks pretty cool. All right. And again, just to remind you, the chaotic nature of this simulation. Let's just kind of look at that animation again. Get a better view. That for that, again, chaotic assembly motion, we're getting real good agreement. You're seeing right at the end that they begin to separate. Right? And so they all kind of look like that. And just to kind of, again, talk about kind of the chaotic nature of this, let's let it run for 4 seconds. And you see that things do depart. And so as soon as they depart very rapidly. And that does put a little bit of a challenge. I'd say I'm already pretty convinced that we got it. Yeah, the models are equivalent. But I think the next video, because it's going to lend itself to an important thing to talk about too, is that I'm going to validate that the relationship between forces and torques and the movement is correct. And the way I'm going to do it is I'm going to choose the motion, with my PVA type of signals, and show the same, torques would be calculated, right? And anything that's kind of unstable and it's a solution to a second order differential equation, I think you need to be a little bit creative on how you're going to validate it. And I think this will be a good way to do it. Okay. Anyways, thank you.